Hello, we're Team 77. I'm Austin.
I'm Rajay.
And I'm Tyler.
And this is Exploration Station. Alright, in this DP3 video, we're going to talk about concept development, which includes FMEA, design for environment, product architecture, and industrial design. We'll also talk about system level design, detail design, and discussion of future changes, economics, and we'll finally finish off with a conclusion. Alright, first of all, we did a complete failure modes and effects analysis on the BRG. And right here we're going to cover just one mode of failure for each obstacle. So for the balloon rocket lift, a mode of failure was the balloon. We found that there were times that it would just pop, and most of that was due to it getting caught with the pin at the very top, or maybe getting stuck on the inside of the tube. The RPM for this failure mode was 32, so kind of right in the middle there. Not super important, but we're still something we wanted to fix. So as a fix for that, we tried to look into stronger balloons or using some kind of lubricant or something inside of the tube. Next, the moon puzzle. A mode of failure for this one is the piece insert, and we have an RPM of this one of 30. So basically, the piece can be oriented incorrectly in the moon puzzle, and it will cause the ball to get stuck like right in the middle. So the way we fix it is we put an arrow on the piece of the moon puzzle to show which direction is up, and then that ensures that the user puts in the piece the right way. The ball will go through. And the last obstacle, the failure mode, was the axle for the turning wheel. The RPM for this is 16, and basically this failure occurs when the axle slips on the motor shaft. And this, as you can see, the RPM is pretty small, so this doesn't occur as often. And as a fix for this, we just made it a tighter fit on the motor shaft.
Alright, so as a team, we really wanted to push the green agenda, and something that would push it, motivate us even more was cost reduction. We could reduce the materials as well as reduce waste there. Also, as a more informed public, the market demand has changed for greener products. So some of our goals are to reduce materials, reduce the waste, extend product life, as well as promote recycling of each obstacle. We can attain these goals by 3D printing each of our obstacles. We're going to use acetyl resin. That will reduce waste as well, and we want to compact our packaging so that will fit more BRGs within the truck and reduce the number of trips it has to make to the distributor. Extending product life, we want to make the motor smaller and shrink the size of the propeller. That will expend less energy from the battery, as well as being easier to maintain, so that we could change up the balloon lift to something that's more sustainable, as well as recycling material. Acetyl resin is a recyclable material, so any leftover from 3D printing, as well as once the product's been through its whole life cycle, people can remove the pieces that are recyclable and just drop them. Overall, this promotes environmentally friendly products, as well as it pushes positive images for the exploration station. For product architecture, we basically have three components to our product. We have the moon puzzle, we have the balloon lift, as well as the turning wheel. For the rocket lift, which has the balloon inside, we could change that to a sophisticated blower motor, so we would basically take out the balloon. Currently, we just have a hand pump pushing that. For the moon puzzle, we have two possible outcomes. Currently, we have an insertion piece. Another variation to this is we have a motor control a gate that would just lift up a gate and control if the ball can move through or not. And then turning wheel, we have three different options. Each variation would get more sophisticated with the program, as well as the motor, and more realistic design. So overall, our industrial design, we believe that our user interface is medium to high rating. The aesthetics are pretty high. The space theming is pretty popular with younger kids, and the ability to maintain and repair it is pretty decent. The balloon's probably the hardest part to fix. It's hard to reach inside of the tube. Appropriate use of resources, we believe is pretty medium. We believe we could change out the foam for something that's more recyclable, also hollowing out the obstacles, as well as changing the tube to something that's shorter or something that's collapsible. And product differentiation, we don't see anything like this in the market currently.
Alright, so we have a CAD of our entire BRG that was built on Autodesk Inventor. As you can see, we have the rocket lift, which as the balloon rises, it hits a pin, which knocks the ball on a ramp and pushes it down a secondary ramp, which pushes it through the moon puzzle, which the answer had already been provided, and goes down another ramp, which goes into the turning wheel, which then the student needs to answer a question. And if the question is answered correctly, the propeller fins and the propeller assembly will turn, allowing the ball to line up with the hole on the end and exit on the exit ramp. We also have an entrance ramp in the beginning that intakes the ball from any other BRG that it could possibly be hooked up to.
And now we have a video animating how this is functioning.
Alright, so now we're going to go over the CAD of the main BRG components. This is the CAD file for the moon puzzle. This CAD file is important because this would be given to the manufacturer at the manufacturing process, and this is what they would base their product that they're building for Exploration Station off of. This would be a template or a blueprint for each moon puzzle that comes out of the manufacturing process, no matter what the differentiation is. And this is a CAD of the main BRG component, which is the turning wheel, and this includes the propeller fins and the propeller assembly, as well as the base of the UFO turning wheel assembly and the exit ramp. And this is the rocket lift CAD file, and it includes the hole where the manual hand pump is inserted, as well as the cylinder in the center and the assembly on the top that holds the ping pong ball, as well as allows it to tilt and go onto the secondary ramp.
Alright, so now we're going to talk about some future changes that we would make, especially as we're approaching the manufacturing phase. So we wanted to have a main focus on the design for manufacturing. So basically, foam, which is what we use for prototyping, is not really a good material when we push into manufacturing. It's expensive, it's hard to work with, it's messy. So we kind of decided on acetyl resin, which is a cheaper option to foam. It's easier to manufacture, you can actually 3D print it. And we could end up making almost all of our obstacles out of that material. Another main change for the future would be switching from the Arduino Uno to a simpler circuit board. That would be much cheaper. Basically, we don't need all the functions that the Arduino Uno offers. We only need it to turn the axle of the turning wheel. So all those extra features are just extra costs that we don't need. So if we just eliminate that, then we can cut costs drastically for the entire thing and even sell it at a cheaper price, which makes it more readily available for teachers and schools alike.
Alright, so
So for the assembly time worksheet, we looked at the worksheet to see how long it would take for handling manual insertion and the total time it would take taking the Exploration Station out of the box to putting it together. Of course, these times have no pauses, so just look at it and see what the parts actually look like when they're together. But using this table, we had decided that the rocket lift, it would take 3 seconds handling it to put it in the place that it needs to be. This is due to the use of 2 hands, as well as the size of it in order to put it in its place, as well as a manual insertion time of 1.5 seconds in order to put it into its correct position and make sure that it's secured. And this would have a total time of 4.5 seconds. We also said that ramp 1 would take another 3 seconds due to its shape and where it needs to be put in the BRG. And we have a manual insertion time of 2.5 seconds, which has a total time of 5.5 seconds. And the moon puzzle, we said would take another 3 seconds to handle it and 1.5 seconds to manually insert it. And that would take a total time of 4.5 seconds. Ramp 2 would take 2 seconds for handling since it's a less sophisticated design. It's very simple and easy. And it would take 2.5 seconds to manually insert it. And that would be a total time of 4.5 seconds. And then the turning wheel, which would take the most amount of time, has a handling time of 3 seconds, but it has a manual insertion time of 5 seconds due to the size and the amount of wires with the Arduino hooked up to the underneath of it and to the motor propeller assembly, and that would have a total time of 8 seconds. So Team 77 decided with these calculations that it would take approximately 27 seconds to build Exploration Station out of the box. We also did a cost sheet for Exploration Station, and we had decided that it would take 1.25 pounds of acetyl resin in order to build all the parts necessary, including the moon puzzle, the turning wheel, and also parts of the rocket lift. And we found that acetyl resin is approximately $3.23 per pound, so that would cost $4.04. We also said the Arduino that we would use until we get enough orders that we could find a cheaper option, and that this would be something that our consumers would like. And that's $24.95, and that's one of the most expensive things on this list due to the complexity of the Arduino Uno. We also have the breadboard, which works in conjunction with the Arduino, and that's $3.69 a unit, and we only need 1 unit per BRG. We also have the clear tubing for the rocket lift, which we would need approximately 2.5 feet of it, and that would cost $1.38 per foot, so that would be a total cost of $3.45, as well as the DC motor and the pump assembly, which together would be approximately $4.95. We also had to look at the fixed costs, which would be the mold tooling for the moon puzzle as well as the turning wheel, and we believe that it would cost approximately $50,000 to get a mold tooled for the moon puzzle due to its simplicity, and $60,000 for the turning wheel also due to its simplicity, since it is a very simple design and it doesn't really take a lot of tooling, and it doesn't have really any interior cavities that would require an extra amount of tooling. And we said that we could get approximately 500,000 units for the first mold for the moon puzzle, and approximately 750,000 of the turning wheel. This is just due to the amount of surface area that both of them have, and also the design of them in general. And so the moon puzzle will cost about 10 cents per unit, and turning wheel will cost about 8 cents. So our total cost is $41.26 per BRG.
Alright, so in conclusion, across the semester, we basically developed a product that has multiple years of use. We've done a failure modes analysis. We've looked at it, any ways that we can make it environmentally friendly. We've worked on the CAD drawings and gotten complete assemblies in Inventor, and we discussed some future changes that we can make to advance on our product, as well as any economic analysis for funding and return on investments. Thanks for listening.